This math-based video on vectors and trigonometry. If we will review a little bit what a vector is and how we used it in translations and how we'll now use it with relationship to trigonometric situations. So we talked about previously how a vector has two measurement quantities. It has magnitude and it has direction. Unlike most measurements like length, which will just be length, a magnitude, or degrees, which are just a direction, a vector has both of them together. And it has unique properties which allow it to be really applicable in physics. So the magnitude of a vector is indicated by the length of the vector. Right? It represents the strength of the quantity being measured, whether that be in translations, where we talked about the magnitude being how far all the points moved, or in this case, we'll be doing some problems where the magnitude represents the velocity of something or the force being applied. So we're going to use vectors in a more sophisticated sense. The direction of the vector usually involves an angle of some type. So we're going to use vector directions which are similar to those in the unit circle, where we have degrees from the positive x-axis. We will also use some compass direction vectors, where we'll talk about things like how many degrees east of north or north of west. You're going to need to be able to, first of all, change between component vectors and polar vectors. So the component vector is what we used in the past with translations, where we have a comma b, where a and b are the terminal point of the vector and 0, 0 is the indicated initial point. Sometimes the vector will be given with both points, where 0, 0 is not the initial point. You'll notice the difference because if it's a component form, it just has the pointed parentheses. If it is just regular coordinate points where they give you both the beginning and the end of the vector, they will both be indicated with regular parentheses like any coordinate point. Any vector not given in component form, we will probably find it most useful to change it to component form by translating it to the origin before working with it at all. So that's the component form of a vector, where basically we have x and y coordinates. Polar form is what's going to be a little new to you, but we can connect it to what we previously did with the unit circle, where the format is going to be r theta, where r is going to be the length of the vector, the magnitude of the vector, which is essentially the length of the radius of the circle. And theta is the angle between the vector and the positive x-axis. So we can go anywhere from an angle of 0 to 360 or 0 to 2 pi. At times when we're doing navigation problems, we will want to give compass directions. So again, we may not say something like 300 degrees from the positive x-axis. We may say it's 60 degrees south of east. So it just depends on the context of the problem, which would be more appropriate. So here's a simple example. I think I've created about 6 examples for us to work with on vectors. Some of them I'll do with you, and some of you I'll ask you to take a try and do them by yourself. So the first example is we have a vector, -2, 5, and we're going to practice writing it in polar form from the component form. So if we draw a picture of the component form of this vector, -2, 5, looking something like that, with a terminal point at -2, 5 and an initial point at 0, 0. We will do the same exact thing we did when we were working in the unit circle. To write it in polar form, we want the radius and we want the degrees from the positive x-axis. We will drop an altitude to the x-axis and work within our familiar right triangle. Since this point is -2, 5, that means this distance is 2. For all purposes of length, even though it is negative, indicating direction, and 5. You can see that the radius for polar form is easily found with a little bit of Pythagorean theorem. R squared equals 2 squared plus 5 squared. R squared is 4 plus 25, so R is equal to the square root of 29. That is the length of the vector. Now, if we had a situation where a decimal was more appropriate, we can see that's about 5.4 in length. So in writing our polar form with r theta, we easily have the r as square root of 29. The degrees we can find with any trig function. I will use not the radius because it's been rounded off. I'll use tangent. So to get this theta reference angle, I will do tangent inverse of 5 over 2. So theta reference equals tangent inverse of opposite over adjacent. Take my calculator and do my inverse tangent function. And I find the angle is 68.2 degrees. Now that is just the reference angle, how many degrees it is from here to 180 degrees. If I want the degrees from the positive x-axis, which is 0, I will say, okay, well, all the way around is 180, so I'll subtract my 68.2 degrees and see what's left. So that means our vector terminates at 111.8 degrees from the positive x-axis, which is more than 90, and a little bit more after that, 111 degrees. And there we go. That is our polar form of the vector. Which, by the way, is the magnitude and direction, just in case we're doing some kind of application scenario in the future. So here's a different vector. This time, instead of just giving you the component form, I'm giving you the beginning and the ending coordinates of the vector. So we may have to translate it to the origin. So this vector has the point -7, 2. And the y point is 2, -1. Okay. Well, the vector is going from x to y, so really the vector is going this way. When we did translations, we discussed that any vector with the same direction and the same magnitude would be equivalent to this vector, including a vector that begins at the origin. This vector goes from +2 to -1, so basically it goes down 3. It also goes from -7 to +2, which means it goes over 9, which means the vector right 9 down 3 is equivalent to that vector. If I go right 9 down 3, I will have a vector with the same direction and the same magnitude. So why don't I work with that vector and find its polar form, which would be equivalent to this one? So if this vector goes right 9 from -7 to +2 and down 3, I can find the reference angle from 360. I can also find the magnitude with the Pythagorean theorem as I did in the previous problem. I would encourage you to pause the video now, try it on your own, and then come back and check. All right, so to get the magnitude of the vector, I'll do a little Pythagorean theorem. I'll just call this vector v. All right, so vector v, which is going to be the same as vector xy, is the square root of 9 squared plus 3 squared, the square root of 81 plus 9, so it's the square root of 90. We could get the simplest radical form of that. 90 is 9 times 10, so that would be 3 roots of 10, or some decimal approximation of about 9.5 when I find square root of 90 on the calculator. So that is the radius of the circle in which that vector moves on as we go all the way around the coordinate plane. And the degrees, theta reference, tangent inverse of 3 over 9, which is the same as tangent inverse of 1/3. We're looking at an angle of 18.4 degrees for the reference angle. Now that's 18.4 degrees below a full turn. If we go from the positive x-axis, okay, we're talking about going 90, 180, 270, and a bunch more, almost all the way around a full circle, minus 18.4 degrees, which means I can take 360 and subtract 18.4 degrees. which means the angle is 341.6 degrees. So the r theta for this vector would be 3 roots of 10, comma, 341.6 degrees. Okay. Now let's just notice this has been some kind of navigational problem in which we had north, south, west, and east. We could say that it's 18.4 degrees south of the easterly direction, and that would be a compass direction. Next example. Now we're going to find the component form if we're given the magnitude and direction. So in this example, we have a vector with a magnitude of 11 and a direction of 225 degrees. A little blurry here. My camera's slow to adapt to movement. So I am going to go 90, 180, 225, which is before 270, with a magnitude of 11. So if we're looking at that right triangle, we should be able to find, oh, there we go. Now we have the visual. If we're going 90, 180, 225 is exactly 45 more, which means we're looking at a 45, 45, 90 right triangle. We could do special right triangle rules, and we could do traditional trig. I'm going to do special right triangle rules just to get accurate answers, in which the component form, we're looking for the x and the y coordinate that terminates at the end of that vector. I take the hypotenuse, I divide it by square root of 2 to get the length of the leg. If you're asked to rationalize, you would rationalize, and we get 11 square roots of 2 over 2. Now, because we're in quadrant 3 here at 225 degrees, our component form must as well indicate that, which is why we go negative 11 roots of 2 over 2 and negative 11 roots of 2 over 2. And that is the component form of that vector using special right triangle rules. I think it's interesting to note here that when we did it on the unit circle, we had a radius of 1. And since we know all circles are similar, a circle with a radius of 11 is exactly 11 times bigger than a circle with a radius of 1. And then previously, when we did our special right triangle rules, we had negative square roots of 2 over 2 and negative square roots of 2 over 2 for 225 degrees. This is a circle which is 11 times bigger, so its coordinates are 11 times bigger than the previous distance. Just kind of interesting to note how the fact that all circles are similar kind of relates to this. Example 4 out of 6. We're going to find the component form of a vector representing the velocity of a boat. So we're still finding the component form, but we're using some compass direction. The boat's traveling 30 kilometers per hour. That's the magnitude of the vector at an angle of 30 degrees north of west. We have another special right triangle situation that we can use. So if we're going north of west, that means if we start out going west, we go 30 degrees north of that. So that means our vector is essentially at 150 degrees. It could be worded that way. So the boat is traveling 30 kph. I would encourage you to find the component form of this vector on your own without me, and then come back and check it. So looking at this one with my special 30, 60, 90 rules, I know that the short leg, which is opposite the 30 degrees, is half of the hypotenuse, so that is 15. And the long leg is the short leg times the square root of 3, which means my component vector would be negative 15 square roots of 3 because I go left, and then positive 15 because I go up, and there we go. It's decimal, or I'm sorry, the simplest radical form of that vector. Next example. Okay, this is example 5. We have a boat attempting to cross a river at 25 kph, while the current of the river is flowing south at 7 kph. So we're going to have the boat attempting to cross the river at 25 kph. We're going to assume it's going east. We'll have to talk to the author about not telling. And the river is flowing south at 7 kph. So this is an application problem in which we are going to find the speed and direction of the boat and what the rower can do to counteract what happens to the boat. So in order to find the resultant vector for the boat, I'm going to do the parallelogram method, and I can see that this is the resultant vector. So basically, if we're going 25, 0, and 0, -7 as the component form of the vectors and adding them, we can see that the boat goes 25, -7. So to get the direction of magnitude, magnitude is easy because that little Pythagorean theorem will get us the magnitude. So it will be the square root of 25 squared plus 7 squared. The square root of 25 squared is 625. 7 squared is 49. So about 25.96 or 26.0 kph. So the boat is going a little faster because the resultant vector is a little longer. The degrees south of east will be the direction. So to get the reference angle, it's going to be tangent inverse of opposite over adjacent. Let's calculate that. Second tangent of 7 divided by 25. I get 15.6 degrees. That's the angle right there. So we can say the boat travels 15.6 degrees south of east at 26 kph. To address the question of what can the rower do to counteract these results, the rower can counteract being pushed 15.6 degrees down by pitching the front of the boat or the bow of the boat 15.6 degrees up so that its overall trajectory will end up where it wanted to go in the first place. The rower should pitch the boat 15.6 degrees north of east to counteract the current. And that's the end of the solution to example 5. Okay, for our last example, example 6, we have a plane taking off at a velocity of 130 miles per hour at an angle of elevation of 10 degrees north of east. There's a wind blowing directly east at 15 miles per hour, so we're going to find the speed and direction of the plane. This is going to be a multi-step problem because, as you see, our original vector for the plane is given in terms of r theta, more of a polar notation, rather than a component form. And we need to add that to a vector for which we know the wind is blowing directly east at 15 miles per hour, which is the vector 15, 0. So in order to add them together, I need both vectors in component form. And I don't have that right now. So I'm going to take the original vector, the 130 and 10 degrees, the original trajectory of the plane, and change to component form. So if I look at just that one, 130 and 10 degrees, and drop my altitude, I can do a little basic trig to get the x, y coordinate to go in the component form. So I know that the sine of 10 is equal to y over 130. And the cosine of 10 degrees is equal to x over 130. Cross multiplying gets me my y-coordinate and my x-coordinate in this situation. So let's do 130 sine 10. And I can see 130 sine 10. 130 times sine 10 is 22.6. And 130 cosine 10 is 128.0. So I have my component xy form as over 128.0 up 22.6. So now that I know the component form of both vectors, I can add those vectors together to get the component form of the resultant vector, which is going to be 128 plus 15, which is 143, 22.6 comma 0, which is 22.6. So that is the component form of the resultant vector. It is 143, comma 22.6. So now I'm just going to look at the resultant vector at the 143, 22.6 separately so that I can calculate its direction, degrees, north of east, and its magnitude or length. So to get its magnitude, I will find that by doing the square root of leg squared plus leg squared, so that I can calculate that. 143 squared plus 22.6 squared, the square root of 20959.76. I get about 144.8. So the new speed of the plane is somewhat faster. It's 144.8 miles per hour, which is increased from its previous or its initial speed of 130 miles per hour. Ends up moving faster due to that wind. And for the degrees of the reference angle, I will do tangent inverse of opposite over adjacent. Second, tangent of 22.6 divided by 143. And I get 8.98 degrees, so approximately 9 degrees. So what happens is that wind going directly to the east brings the angle down and speeds the plane up, just as the parallelogram addition method of the vectors would show for the resultant. So the plane travels approximately 9 degrees north of east at 144.8 miles per hour. That is the overall resultant speed and direction of the plane.